In the year of Galileo's death, the prodigious Isaac Newton breathed his first breaths of life. Newton simultaneously invented calculus alongside Leibniz, as well as discovered the laws of gravitation and motion, while all along making great advances in the field of optics. Taught in every introductory physics course across the world, Newton's laws of motion define the concept of force and the ideas we know today as dynamics. But let us consider Newton's third law, which states, to every action there is always opposed an equal reaction. Or more commonly said, for every action there is an equal and opposite reaction. But what led Newton to this law of motion? In the Principia, Newton observes that when you press on a stone with your finger, the stone pushes back on your finger. Newton then considers the example of a horse pulling a stone with a rope. But let's consider something that's completely analogous but a little more interesting. When we observe a muscle-bound athlete pulling an airplane with a rope, we can see that the man here is pulling on the plane, but the plane is also pulling back on him through the very same rope. To go further, one would hypothesize that the forces must be equal in magnitude, otherwise the rope connecting the man to the airplane would not remain taut, neither snap or go slack. Newton's third law can be posed in an arguably better way which avoids the ambiguities of the terms action and reaction. The book Physics, the Human Adventure by Holton and Brush redefined the third law as follows. Whenever two bodies A and B interact so that body A experiences a force, then body B experiences simultaneously an equally large and oppositely directed force. Or more simply put, the force of A on B has to equal the negative of the force of B on A. Now let us turn our attention to the case of colliding pendulums. Newton's pendulum, or Newton's cradle, are trinkets found on many desks across the world. In the Principia, these colliding balls serve as a perfect test of Newton's third law. If we consider two masses, mass 1 and mass 2, with their masses being equal, and then lift mass 1 to a height of h, and then release the ball, it will strike mass 2. At the moment, though, before it strikes mass 2, it will have a velocity v. Therefore, it has a momentum mass 1 times v, which is the momentum right before it collides. But after it collides, it stops. So 0 minus a positive number is a negative number. So the change in momentum 1, which is proportional to the force, is negative the mass 1 times the velocity. But if Newton's third law is correct, then the exchange of the momentum, i.e. the force, applied from mass 1 to mass 2, has to be the same. Therefore, the change of momentum on 2 must be the same as the change in momentum on 1. So, in other words, the change in momentum on object 2 is m2v. But since mass 1 and mass 2 have the same mass, then it's going to come off at the same velocity, or the same increment of motion, i.e. momentum once again. And all things being equal, the second mass will return to the same height h. Now, of course, when you do this experiment, and Newton even noted, that it doesn't quite make it as far up, but that is due to the resistance of air. So he says in a vacuum, of course, that this experiment would go off perfectly, and mass 2 would reach height h, then it would swing back, and this whole cycle would begin all over again. But we can also consider another pendulum experiment in which mass 1 is twice as heavy as mass 2. So once again, we extend mass 1 up to a height of h, and then release the ball, and it strikes mass 2. So once again, the change in momentum on 1, ending at rest after the collision, but coming in with a maximum velocity v1, will have a change of momentum of negative m1 v1. So, we could predict that since mass 2 is half the mass of mass 1, it will attain a height of 2 times the starting height that mass 1 began with. Or seen here, the change of momentum 2 is m2v, since it ends at m2v2 and begins at rest after the collision. But what is m2? It's a half of m1. So 1 half m1 v2 ends up equaling m1 v1 because of the fact that it reaches a height of 2h. It's clear to see that v2 must be twice the magnitude of v1. All of this goes to show Newton's third law in perfect clarity. But let us consider yet another example, one which is done in freshman labs in colleges across the country, and one Isaac Newton could have been performed. Consider 2 spring scales attached together by the hooks. When you pull on them, let's consider you pull on one with each hand and pull them apart and read 5 newtons on both scales. Well, it's no surprise that you're reading both the same, because of Newton's third law states that they're equal and opposite forces. So one would predict that it's always going to be the same. If you were to attach the left scale to the wall and pull on the right scale, then once again the force readings you would read off the 2 scales would be the same. Just the same as if you had a bodybuilder holding the left scale and a small child holding the right scale, and they pull the scales apart from each other. The scales will always read the same measured force. In reflection, Newton's third law is fascinating in that the idea of opposing forces is quite intuitive, but to state that they are equal in magnitude depends greatly on the first 2 laws of motion. So it's just fascinating how well and how needed the 3 laws of motion are to adequately describe the idea of force.